I do have a question, but I
Go ahead.
can work on it and maybe ask it later if
But
it works better.
that's usually better. But
Mhm.
if it's something simple, you can also just shoot.
This is like about the choice of positive direction for the potential. I'm still not convinced about the negative signs and positive signs that we chose. I solved the equations in Newtonian mechanics and in Lagrangian mechanics as well. So it all comes down to selecting the motion in the clockwise or counterclockwise, because I get
That should not be the case.
If I select counterclockwise, the equation I get is the one that you constructed. But if I selected clockwise, I mean the M2 going down, and then somehow the equation comes out to be the potential should be negative instead of positive. I don't know what makes the difference, but when I construct the equations, it makes a difference.
To answer that, I have to actually see what you did. Right?
Okay.
But to go back to the original question, do you have a negative sign here or not? And I had claimed that this depends on your choice of the direction for Z. I stand by that claim. Now, the one thing to look at this is that what happens really is so it's just the potential energy of the first mass. Okay, I'm not thinking about everything. It's just the first mass. What happens is this goes up or down. Now, as this goes down, I'm fairly confident because in a free fall, its kinetic energy would increase. The potential energy has to decrease.
Exactly.
Okay? So going down, potential energy should go up. Sorry, go down. It should decrease. Now, as I go down, what does happen? So these are constant. What does happen to this number? So let's say I started, -1, and I go to -2, I go to -3, but I can't track -2, -3, -4, -5, and so on. So this is decreasing. Its magnitude, of course, is increasing, but it is decreasing. So this whole thing with these positive constants in front should also decrease, which is what I want. So this seems correct. If I had chosen the other way, then it will be 1, 2, 3. This is increasing. But this is not what I want. So I will introduce a negative sign. If something is increasing, its negative would decrease, which is what I want. I don't see a way around this. So how do you contradict this one?
So my understanding is because we selected the 0 level at the pulley.
Okay, let's choose another level. Would that be okay?
So the problem is here, like as I understand, you put the negative sign into Z, but because Z is the length, it is positive in my understanding.
No. It's not the magnitude, it's the component.
Okay, then that solves the problem. Okay. Now I understand it.
It can have a sign. It's not the magnitude, it's the component. Okay. So this always arises in one-dimensional problem, whether you're using it for the magnitude or the component. I always use component. Right? Okay. Here, using vectors don't make sense, but imagine that this is actually like this. X, Y, Z. Right? This is the component.
I think the problem we had in the previous session was that in the undergrad level, we assigned those Z1 and Z2 to the length of the rope so that it is always
not
positive.
In my class. No, okay. I specifically avoid that. And this is, if you want to see a deeper discussion of this, there is a book, a freshman level physics book by Knight, Physics for Science for Engineers, a conceptual approach, something like that. So it's Damon Knight, the K. I strongly suggest you look at the discussion there. It's very clean. Like in Giancoli and Halliday Racing, they saw sort of confusion. Knight's discussion is very clean. And just for this reason, I think we should switch to Knight. He does other things right as well, but this is, I know this is confusing. I'm also teaching freshman physics. I taught freshman physics many times. It is very confusing. But these are components.
Okay,
not the main.
that solved the confusion.
Yes.
What was the name of the book again? Could you repeat it?
Physics, a conceptual approach, something like that. So it's actually, if you stop by, I have a copy, but you can also find the PDF online.
Okay. Thank you.
Sure. Anything else? All right. So let's go to symmetry. Now we're going to handle this more formally when we come to Hamiltonian mechanics, right? How the symmetries are related to conservation laws and things like that. Already here, some of the terms that we use are going to be kind of meaningless because we are in configuration space, not phase space. But still, it's worthwhile to discuss these now. So this is, of course, the relationship between conservation laws and the symmetry of the system is Noether's theorem. And Noether had an anniversary a few years back. So there was a lot of material coming out. And this has been explained, and you can find a lot of resources. But as I said, we will come to Noether's theorem after we cover Hamiltonian dynamics. And we're going to just do a preliminary stuff right now. So we have an assumption. So we will assume that the systems we are considering are described by Hamilton's principle, completely. This one, to make this more explicit, 1 to 2 Lagrange, just q dot and t dt is 0. The variation of this is 0. Yeah, we're going to assume so. It's like the potential doesn't depend on time. The constraints are polynomial. Blah 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 blah. Okay. Now, when we have n coordinates, we are going to have n degrees of freedom. Sorry, not n coordinates, but we have n coordinates. We're going to have 3n degrees of freedom. But let's say that we have n degrees of freedom. Then this leads to n second degree differential equations. Now, as you probably recall from your differential equations course, integrating a second degree differential equation involves 2 integration constants. So this means we're going to end up with 2n integration constants. And these need to be provided by our initial conditions. And we have exactly 2n initial conditions. All right. So we have n qj's and n qj dots, our initial positions and velocities. As per our assumption, this completely describes our system. We just need these guys. And their initial values are going to give these integration constants, shield values. Okay. Now, so in theory, these are solvable and so on and so forth. But of course, in theory and in practice are completely 2 different things. You may not be able to solve differential equations for some reason. That they can be too complicated. They can be just nonlinear. There's no known integration, or that they could just be really unintegrable. Right? There are many reasons for this. I'm not going to go into this. But sometimes they're integrable. Sometimes they're not. However, even if your equations are not integrable, you can get some information. And this is what we are going to do. For example, we may be able to obtain a number of first integrals. So we can get things like that. So let's say qi, qj, qj dot, and t is constant. Okay. So this is the first order differential equation. So this is called the first integral. Now, the formal definition of first integral requires us to know about phase space. So these are just some quantities that are constant along the trajectories in phase space. So we are not going to formally define now, we can get into phase space, but just know that we can get some first order differential equation that look like this. And some function over here that's equal to constant. And you cannot get this for everything. If you could get this for everything, then your system is completely integrable. You get the solution, but we can get some of this, and that is in fact sometimes enough to say a couple of things about the system. This is especially true if you're switching to some generalized coordinates, which is dividing the behavior of your system into two parts, like the short-term behavior and the long-term behavior. There could be some oscillatory terms, and there could be some growing terms, the so-called secular terms in your system. And then if you can go into coordinates dividing this, just looking at the behavior of the secular terms will be enough, right? Or if you're interested in just the short-term behavior, just looking at the oscillatory terms is going to be enough, right? So this is not completely just, so there's a story of Nasrettin Hoca, right? So he lost his coin in his bedroom, and he was looking for it in the street. And when his neighbor asked why, he said that it's very dark in my bedroom. There's light here. So we're not just looking in the street because it is light there, because there is some sense. This is actually applicable to some problems. We are not doing this just because we can solve this. This is going to have some applications. Though the applications are unfortunately like a month later or so. Now we're going to consider also a system of point sources. Let me write my assumption here. So consider a system of point masses, not point sources, I'm sorry. Point masses. And the potential is just going to depend on their position. It doesn't depend on the derivatives of the positions, it doesn't depend on time. Right? So what does happen in this case? We get del L by I is equal to the partial derivative of the kinetic energy, because the potential doesn't depend on the time derivatives, just depends on the position. And we're going to have mi xi double dot, and call this x, the x component of the particle's momentum. Okay, so this one is expression. So in this simple case, we are going to have momentum, a linear momentum, but just call it momentum, is equal to this quantity, motivates us to generalize the concept of momentum. Yeah, this is the idea here. So it works in this case trivially, but we are going to go ahead and define so-called conjugate momentum. So conjugate momentum with Pj is going to be the partial of L with respect to Qj dot. Okay. So this has a number of names. The name given in the book is generalized momentum. Associated, it's generalized coordinates Qj. Okay. I just call this conjugate momentum to Qj. Or the momentum conjugate to Qj. There are other names. we could call this generalized momentum for Qj, something like that. That doesn't really matter. Yeah. So we just take this. So in case of this, simple potential, this works trivially. This really gives the momentum. But if you move to generalized coordinates, then this Pj does not have to have the dimensions of mass times velocity. It doesn't have to be kilograms meters per second. It can be anything. But still, we're going to call this conjugate momentum, right? So this definition is valid for V not necessarily equal to Ri. So we start with this to get that simple expression, but we're going to keep using it for everything. So for example, or let's not do this way, but maybe Ri dot and T. So it's just a general definition example. That will be from electricity and magnetism. The potential there is a little bit weird. Or the potential energy, I'm sorry. Plus A dot V. Okay. And the px you get there is mx plus q times yes. This q is charge. It's not the coordinate. It's an overloading symbol, but there's no way around this. Charge is always q. So this, if you use this as your potential energy for a charged particle, and this is the correct expression in electricity dynamics. You'll see this. The conjugate momentum that you obtain is going to look like this, even though your velocity is not just a function of, your potential is not just a function of position. You get some expression, and this expression actually resolves the dilemma we had before. Right? The magnetic forces, which are of course present in presence of a vector potential, the magnetic forces do not obey action and reaction principle. And action and reaction principle kind of goes hand in hand with conservation of momentum. Now, this momentum is not conserved. M times Vx, the linear momentum, linear mechanical momentum, is not conserved, but this one is. Because it turns out that this can be associated with the momentum, or in this case, the x component of the momentum of the field. Right? So the x component of the particle is not conserved, perhaps, but the particle and the field together, it's going to be conserved. This is now, if you know this, then you say, oh yeah. If you don't know this, it's good, but I'm not going to explain this any further. This is definitely in Jackson, but it's also probably like the momentum of the field. How you associate this with the momentum of the field? It is definitely in Jackson. It's also probably in Griffiths. But if you need resources to go deeper on this, just let me know. Yeah. I can definitely find it. I'll just stop here and say that this is, in fact, the conserved momentum in this case. Now, another definition that I want to make is for the cyclic coordinates. I already used this expression a number of times. So if a coordinate is missing in your Lagrangian, if the Lagrangian does not contain a coordinate, but it contains its time derivative. So if it also doesn't contain its time derivative, then that coordinate is completely useless. Okay, there's nothing interesting about it. But if it doesn't contain the coordinate, but contains a time derivative, then we call this a cyclic coordinate. The cyclic coordinate. Now, what is the significance of this? Well, if you write down the Lagrange equations, E of del L by del Qj dot is equal to del L by del Qj if L does not contain Qj. If it doesn't depend on Qj explicitly, then this is 0. Well, if the time derivative of a quantity is 0, now remember, this is just Pj, our conjugate momentum that we defined over here, and Pj is conserved. The conjugate momentum is conserved. For exactly coordinate, the corresponding Pj is conserved. Now, this is the usefulness, not here. We are not going to go into too much detail here, but in principle, you can use this to eliminate that coordinate from your problem altogether. You can recast your equations in a way that that coordinate goes away. One example of this that's commonly done at undergraduate level, at least, is removing the going into a coordinate system with the center of mass and the motion about the center of mass, and removing the motion of center of mass, because under the absence of external forces, the momentum of the center of mass is conserved, which means that you can actually eliminate the center of mass coordinates completely from your problem by looking at the motion this way: motion of center of mass plus the motion about the center of mass. But you can do this in a systematic way for other stuff as well. So remember, this is now a generalized momentum. It doesn't have to be the coordinates of anything or the momentum of anything. But if there's a cyclic coordinate, you can eliminate this by using some procedure. And we are going to look at this, but this is mostly done in Hamiltonian mechanics. So again, I'm not going to go into details, but these definitions, they have to come now. I'm just giving you some side remarks. Any questions? Okay. One thing that we do is, of course, to write it this way. That should not be so. I kind of simplified Lagrange equations. If there are some constraints, then you get additional terms here, right? So this assumes that that you can say that this Pj is conserved, and then go ahead and remove that coordinate from your problem altogether. This assumes that you're using proper generalized coordinates, that the coordinates are independent of each other. Okay? So let me write it here. So this is assumption. Qj are independent. Okay? If they are not independent, then there must be some constraints relating them. Then you can't write this equation this way, and you have to. There is going to be some rate of change of this p. And there's a counterexample in the book where you have a constraint. You actually don't conserve this. Okay. And this, by the way, this Pj is constant. This is an example of the first integral. Okay. Again, we're not going to formally define it here, but this is a very simple example. Okay, so these are my definitions that I would refer to. I think I can read this. Okay. Now, let's assume we're going to look at two cases where there's going to be some translational motion or some rotational motion, and we're going to find the conjugate momenta for these, and we're going to look at some conservation laws related to these two things. And we start with the translational motion. So let's assume that the dqj corresponds to. So obviously, this is something infinitesimal to a translation of the whole system in some direction. And I'll call that direction n hat. I'll indicate that direction with n hat. So this could be, for example, the Cartesian coordinates of the center of mass, right? That you can just move the rigid body, the center of mass is going to just move in some direction, but it doesn't have to be. This is something perfectly general. Okay? So what can we what can we say about this? So first of all, let's say this. QJ, yeah, okay. So QJ cannot be in T. Okay, so T, kinetic energy, is a function of velocities. And my claim is that QJ cannot be in T. Why? Or why not? Now you're moving your whole system. What does this correspond to? So there are two kinds of transformations, passive transformations and active transformations. You can describe the transformation in two ways. So instead of saying my whole system is moving, I could say my origin is moving. I'm describing the system this way. Well, the velocities do not depend on the choice of origin. The positions do, but the velocities don't. Right? So this means that T cannot depend on QJ. Okay? Changes in QJ correspond to motion of the whole system. So there cannot be QJ terms in T. The velocities cannot depend on such a coordinate. When this coordinate is changing, my whole system is moving. Does that make sense? I can only see two faces. You guys seem to understand what this is something that requires visualizing.
But Hocam, we said, in the case when the origin is moving,
Mhm.
the coordinates, are also affected by this. However, like the velocity is the rate of change of the coordinates. So,
but this cannot be. QJ dot can be. I'm not saying so. Only QJ. QJ cannot be explicitly. Let's say that. Let's put it that way. It cannot be explicitly in the expression for T. So I switch to some generalized coordinates, and one of my coordinates corresponds to this motion of the system as a whole from one location to the other. Okay? Its rate of change could, of course, affect velocities, but its value cannot, because its value corresponds to where I'm choosing the origin. Where I choose the origin does not change velocities. Because velocities always depend on the relative position, where you start and where you end up. And that vector is independent of the choice of origin. Right? I mean, I think it's worth drawing things here. So I can do it this way. So let's call this R1 and R2. And I can draw their difference vector, delta R. But I could also choose my origin here. So this would be R1 prime, and this is R2 prime. But their difference vector is going to be the same. And the choice of origin changes the position, but not the velocity. Right? This divided by delta T is velocity. This is not very easy. When you like explain it, and then when it clicks, it becomes trivial. But until it clicks, it's like what? It's so.
When you said active and passive,
active and passive transformations just correspond to one is changing your components, one is changing your coordinates. It's.
So I thought the origin had a velocity itself, so that's why.
No.
Okay.
So it's not like Lorentz transformations or anything like that.
Okay. No, then no problem. Thank you.
And as I said, this cannot be in T, but its time derivative, QJ dot, can be in T. In fact, in general, it is going to be in T. It is the velocity of central mass in the example I gave. Okay. Now, we will also assume some property for our potential that it does not depend on the time derivatives or the time itself. Then, of course, if you make so many assumptions, then your equations are going to simplify. Let's write our Lagrange equations. L QJ dot. This is going to be del L by del QJ. So this has to be, because the T part of the Lagrangian doesn't have QJ. It's just going to have V part, so minus del V. So remember, this is just T minus V, minus del V by del J, and this is of course our generalized force. That's just a partial derivative of the potential given here, leads to some force, but in general it's going to be a general force. And this one, on the other hand, is going to be P by dt of partial T by Qj dot, and this is Pj dot, conjugate momentum's time derivative. Okay. So this generalized force is my conjugate momentum's time derivative, F equals ma. This is what this is saying, but it's now for the generalized forces, and those generalized forces are given by the sum if we express everything in terms of our original Cartesian coordinates. I don't know if you can distinguish between my J's and I's. So these are J's, these are I's. Okay, so this is the sum over all particles, and we're now, this is just chain rule, right? This is how we applied chain rule for the generalized force, and this is the definition we used in the very first lecture. Okay, now how to get these expressions. So I want to get something for this one, and I will be able to express this in terms of the applied forces over here. And so presumably this is going to be, so what do you expect? Right, so this Qj corresponds to some motion in a direction, okay? And so there's a corresponding generalized force that's given by this expression. So I'm going to manipulate this and get another expression. But what would you expect, just intuitively? And to get your intuition going, the easiest way to think is that this is in fact the motion of center of mass. What does it correspond to if this was the motion of center of mass?
Bulk? No, not in the center.
Well, it is just the component of this external forces, applied forces in that direction, right? So you get the total force, and it should just be the direction of that force, the component of that force in that direction, whatever direction this is corresponding to this this direction n, right? So I should get something like the total force dot n. This is what I expect. Now, how do we go about this? Well, we assume that this corresponds to a translation in that direction, and there is a nice figure in the book that helps visualizing this. But if I draw it here, it's not going to help because of the way I draw things. But so I'll try to write it this way. So my Ri that Qj plus dQj. So when I carry out, so in my generalized coordinates, I start at Qj and I go to dQj. This corresponds to a translational motion. This corresponds to taking my original position and shifting it by some infinitesimal amount. Right? And that is going to be, the infinitesimal amount is along some direction. And let's make this infinitesimal. So this expression is just this thing using symbols. Now, what does it say? If I change my generalized coordinate by dQj, then my position changes by some infinitesimal amount in some direction n hat. Okay. As I said, there's a nice figure in the book. Right? So if the mechanical expression doesn't help, then now we get the figure. Now, what is this? Del J, along with this expression. What's the derivative of Ri with respect to Qj if the dependency of Ri on Qj looks like this? Now, this is a derivative. Now, what is the derivative? You take a value, you take a value in a neighboring point, you take the difference and divide by the distance, right? So, if you do it this way, so x prime is x plus or x plus dx minus x over dt, something like that, right? So you take the little disturbance, multiply, subtract from this the original value, divide by the increment you get, right? Or we write this as f prime of x is f of x plus h minus f of x divided by h. Perhaps you have seen this one, for example, in computational physics and things like that. But this is the definition of derivative, right? So, f prime is the definition of derivative. Yeah, this is going to be n hat. Right? You move this to the other side, you get the numerator. You move this to the denominator, you get the derivative. Right? So this minus that divided by dqj should be the derivative of r with respect to qj. And so this is n hat by definition of derivative. This is, but I can take this and head out. Fine. Because dot product just distributes over addition. And this is the total force. This is n hat. This is just the component of the total force in that direction n hat, which is what we said. So this is one result. That's nice. I also want to show something about the momentum, and for that I'm gonna make some room again. Just here. Now my t is a half. Is it mi? Yeah. Mi vi dot vi. I'll write this, of course, p squared, but I want to be a bit more explicit here. And my pj, my generalized momentum, is del L by del qj dot. But this is, as we have seen, because the potential does not depend on the time derivative of the coordinate, it's just going to be qj dot. And what's this? So how do I express this in terms of things that I already know? Chain rule. Okay. You got to apply chain rule. So you take this one. So I can't take the derivative of this with respect to qj, but I can take the derivative of that with respect to r's, and then I know the derivative of r's with respect to qj. There is some manipulation. We just need to go through a couple of steps. And this is going to be just mi vi dot del vi by del qj dot. Okay. And this one is sum mi vi dot del ri by del qj without a dot. So this was the derivative of the velocity with respect to the time derivative of the coordinates. It is equal to the derivative of the positions with respect to coordinates. I think this was your homework, right? To show that this is in fact true. It's just an application of chain rule, but something very handy. And now this is just n. So this generalized momentum is in fact the component of the linear momentum along this direction. Right? This is the total linear momentum. And so this is the second result. The generalized force corresponding to this kind of coordinate is the component of the total external forces along that direction, and the conjugate momentum corresponding to that coordinate is the component of total linear momentum in that direction. Whatever direction, along whatever direction this coordinate is generating, so to say. Okay, I don't want to use big words like generators and so on and so forth, but you might as well say. Okay, so one thing we can do is that if this coordinate is cyclic, then this is going to be conserved, right? But if that coordinate is cyclic, then the force is going to vanish. Right? So this is again the relationship between the conservation of momentum and the lack of forces. But this kind of, this is kind of intuitive that there's some force. If there is no force, that leads to some rate of change of momentum. If there is no force, of course, there is no rate of change of momentum. It's just conserved. But here we did this completely, independently. These results are not derived from one the other. Okay? So you can state this as an independent result and then say that F is in fact equal to MA. Right, now I want to do one more example over here. Are there any questions about this? These two results? Okay. Now, the other one is when the change in QJ corresponds to some rotation. And that's, of course, a lot of fun. Now, here we have linear momentum. I think you would totally expect that if you have rotation, then you're going to have angular momentum, and we do. Let's show that. So let's assume, say, dqj corresponds to some rotation around an axis. And head. Now, T again cannot depend on QJ. Okay. Now, why T cannot depend on QJ? Because T, the way it is written in the original Cartesian coordinates, depends only on the magnitude of the velocities. A rotation changes directions, but it doesn't change magnitudes. It cannot depend on QJ. Again, it can depend on QJ dot. It can't depend on QJ. Right? And again, we assume that V is just V of QJ or QI, let's say. It doesn't depend on the time derivatives. It doesn't depend on the time explicitly. So we can get, I'll just skip some steps here. Our conjugate momentum is going to be just the generalized force as defined, through this. Let's write that down. By J. Okay. Now, how would you write? So with the translation at this step, we wrote some expression for R. So again, let's try to write an expression for R for QJ plus dQJ. QJ. So the sort of rotated positions. So this is going to be rotated RQJ. Right, now I have to try to make it rolling here. It's just no way. So this is going to be my n head. I'm going to be rotating around this vertical axis. You could call it z-axis, but this is my n head. And I start with some point over here, let's say, and I rotate around this. So let's put a circle that passes through that point. Okay. And I will like rotate this much. Okay. So this is my R of Qj. And this one is my R of Qj plus dQj. Qj. So they are moving on a circle. And so there's going to be some angle for all the points on the circle theta. So this is the angle that my position vector makes with the n head. So angle B R and n. And this doesn't change after the rotation. I'm just going on a circle. All the points on the circle, in fact, makes this angle theta with my n axis. So you gotta write some equations. So this is, I would just be repeating the equations that's written in the book. Okay, so I'm not going to do this, but the end result is going to be that let's just write stuff in the book, not leave everything out completely. Del Ri over del Qj, in this case, the expression that you're going to plug in there is not going to be n head, but it's going to be n cross Ri. Okay. And this comes from like writing this equation. So you look at this as some rotation over some angle dQj, and you write down the expressions for the chord length or the arc length that corresponds to this motion. Okay. But it is really in the book, it's just one page. I don't want to write these down. And then the generalized coordinates, the generalized force, sorry, that you get is going to be n dot the total torque, and the coordinate, the generalized momentum that this corresponds to is going to be n dot angular momentum. Okay. So this is the result you get for this problem. As I said, there are some equations, but I want to say a few things and just finish this without taking an additional break if possible. What is the result you get? So this is, in fact, what you expect. For rotational motion, you're going to get the generalized force that is the component of the torque along this rotation axis, and your generalized momentum will be the component of your angular momentum along the axis. Okay. And the manipulation of the equations is pretty much the same, all the steps, except you have to really use some different geometry, and you recognize at some point that, oh, I have this sine angle here, and then so it has to be a cross product, and you just proceed from there. Okay. So once you get this, this is of course, it follows immediately. Right. Now I want to talk about the energy function. I'm not going to ask if you have questions over here, because I skipped over a lot of things, but the main formalism looks like this. I just want to say some things about the energy. How are you doing, though? Do you want to take a break, or shall we like go on for another 15 minutes and try to finish? Yeah. Does anyone have a problem with continuing for another 15 minutes? Is there anyone writing anything in chat? No. All right. I'll just go on then. So momentum, angular momentum, the last thing that you want to deal with is, of course, energy. Okay. And let's just consider the general Lagrangian, which is function of Qj, Qj dot, and T. And then we're going to kind of restrict this its properties, but let's start with something general. So what's the time derivative of this? dl by dt. Well, you apply chain rule as usual, and so you start with I del L by del Qj by del T plus I del L by del Qj dot and del Qj dot by del T plus L by del T. So you can take this and manipulate these. Again, it takes a couple of algebraic steps, and you get I d by dt of Qj dot by del L del Qj. What's this guy here? Now I can take this one and move to the other side. There's a total time derivative here. There's a total time derivative here. So I can kind of collect those terms and say d by dt of the sum of Qj dot and the partials of L by Qj dot minus L plus partial of L by LT is going to be 0. Okay. Now, if your Lagrangian explicitly depends on time, there isn't anything you can do. Okay. You don't have anything conserved. But if it doesn't, then this thing here that we'll call H is going to be conserved if Lagrangian does not explicitly depend on time. Yeah, let's put it this way. Partial of L with respect to T is 0. This is in fact both a sufficient and necessary condition. Okay, so if and only if this H is so let's write this H down in this form. So this is Qj dot, and this is Pj, right? So this is the partial of Lagrangian with respect to Qj dot. So we already defined this to be conjugate momentum minus L. Now this in value is equal to the Hamiltonian function. This is in fact how we are going to define the Hamiltonian. Right? But here, or I should put equal. Here we are writing everything in terms of just the coordinates. Okay, we are not using the conjugate momentum, but eventually we are going to define our Hamiltonian this way. The difference between them is that we are defining different spaces. This one is defined in Q dot space, that's a tangent space, or tangent bundle, whatever. This one is in phase space, the symplectic space. They have different properties, so they're going to lead to different results. They are, of course, the same, but at the same time distinct. Okay. They have different utilities. So in the book, they say that they say this is sometimes called the Jacobi integral. The only time I heard that being called the Jacobi integral is in context of celestial mechanics, and in particular the reciprocal three-body problem. But Goldstein is also someone who's very interested in the history of classical mechanics. So if he says that there's some precedent to call this Jacobi integral, I'll give it that. But we'll just call this energy function H. Okay. Well written in this form. Okay. Yeah. So this is already something useful. Do I want to go into? So we can write our kinetic energy in this form. Okay. So this is something that was earlier in the first chapter. I kind of skipped over this. Perhaps I shouldn't have. So this one, this form is this is linear. Sorry, this is just a function of Q. This is linear in Q dot, and this is quadratic in Q dot. Q dot. So it turns out that you can always separate your kinetic energy this way, and if your transformation function, if the function that takes your original Cartesian coordinates into your generalized coordinates do not involve time, then you're not going to have T0 and T1 terms. It's always going to be a homogeneous quadratic function in generalized velocities. So this is not obvious, but this is something that we are just going to take. So for our problems, if transformation is independent of time, then T is equal to T2. Now, in a similar fashion, we can write our Lagrangian in a way that's L0, this is just Q and T, plus L1, this is Q dot and T, and L2, Q dot and T, and this is a linear homogeneous function. Of Q dot, and this is quadratic homogeneous function of Q dot. Now, what does this mean? What does a homogeneous function that's linear in something or quadratic in something mean? This is the only point I want to make. The rest is just algebraic manipulation. So you heard of homogeneous function before?
So when we take everything on one side, in the opposite, if we have zero, no constant, let's say, then I mean, I recall this from differential equations, but that was
it's in linear algebra, right? When you're writing linear equations, so they could be homogeneous or inhomogeneous. And it is what you call it, what you just said, if there is a constant term or not, if there are additional terms or not. So these should not be, functions. So this is just depends on the second power of Q. There's no linear term, there is no constant term. It just depends on the first power of Q dot. There's no linear term, there's no quadratic term, there's no constant term. Okay. So this is what they mean by this. The nice thing about this is that for these homogeneous functions, there's a theorem due to Euler. So if f is a homogeneous function, of degree n in variables I and I. Okay, there's this theorem, and you take this and apply it to the expression for the energy function. So just let's recall this energy function. This was Qj dot del L by del I No, not X, sorry. QJ. Dot. Then you divide your Lagrangian into these parts and use this theorem to obtain what these would look like in terms of the original functions themselves. And for the h, you get from this partial derivatives and so on and so forth, 2L2. Right? So this is the quadratic term plus L1, L0 of course goes away, and minus L thing over here. And this is because L is just L2 plus L1 plus L0 is L2 minus L0. And T0 and T1 are 0, so this just comes out. So what this comes to? So T is just going to be T2. Your H, after the algebraic manipulations, becomes just theta plus V, okay, total energy. And in this case, it's going to be, so if the Lagrangian is not an explicit function of time, it's also going to be conserved. Now, the point of this, that we are going to take this and manipulate this next time. So this function is going, the utility of this function is going to become more clear. I think when we look at celestial mechanics, but we did not. So the two properties of this, that the H is conserved, and H under certain conditions corresponds to total energy, are independent of each other. Okay. And this follows from that you get this result, that you have a function that corresponds to total energy. Yeah, this is the way to put this. And that function is conserved. So the conclusion is total energy is conserved. It depends on the fact that there is no time dependence in your explicit time dependence in your Lagrangian. We did not use this to get that it is conserved. It is conserved. I mean, I erased this, but you remember that there was this function with the partial derivative of L equals 0. It is conserved and there's no explicit time dependence. So this is completely independent of the fact that this, after all these algebraic manipulations, which is just go to the book and follow it from there. That there's really, it's not complicated. That this corresponds to total energy. They are independent of each other. This is critical. We are going to do something similar with the Hamiltonian. Right, so Hamiltonian is also going to correspond to total energy. And for our purposes, it's not very important. But if you go to things like extended phase space, that's something Shahin asked about at some point, then it is going to be important that this is a conserved quantity, but then it's not conserved because there's time. And then how do you go back to something that is conserved, which is not really energy? Okay, it is the Hamiltonian in the extended phase space, so it doesn't correspond to total energy, but it is still conserved. So it is going to be more useful than all this will make sense. But the whole point of this exercise is that the fact that this corresponds to total energy and that it's conserved, they're independent. They both follow from the properties of Lagrangian we assumed. So you can make these algebraic manipulations and get this to be total energy and show that the total time derivative of that is 0, but they're independent. And as I said, this is at this point, it's not like, okay, I know conservation of energy, but yeah.
The capital H is Hamiltonian, right? The capital H.
Ya bir sesiniz kesildi. Bir daha söyleyebilir misiniz?
So the capital H is Hamiltonian, right? The capital.
There is no capital H. So
No,
there was a capital H.
No, the one that we have written previously.
Yeah. So that one was Q, just PJ. So Hamiltonian is defined for the phase space. So you have momentum L. So this was Hamiltonian. So this has the same value, but it's not Hamiltonian. It's just defined in the configuration space.
Yes. So the Hamiltonian is Hamiltonian always conserved?
No, no,
So the
No.
same criteria applies for both Hamiltonian and the energy function, right? So
yeah,
okay, so they always have the same value. So it's not something
yes,
like
they have the same value. They're not
Okay.
the same thing. They don't have the same mathematical properties, but that's a very nice way of putting it. Thank you. They have the same value. But
Okay.
just because two things have the same value doesn't mean they are the same, right? Like think of computer programming. You have two variables, they have the same value. Are they the same? No. Are they equal? Yes. Equal and same are different things, right?
Okay. Thank you.